Okay, what we're doing now is it filming? We're having some technical difficulties for those of you who are just joining us from somewhere in ether land, okay? Just see if everything is working here correctly. Looks like it's filming. Okay, good. Now, what I'm going to do is, I have on the board behind me, and it might not be as big as it normally is because I moved the cart back about a foot to 14 inches, okay? Something just happened? Is it all right? I need a videographer. Can somebody see this? Somebody's going to keep an eye on that? Okay. Okay. Now, let's begin. Okay? Let's begin. We're doing a video on states of matter. Okay? And the first section is going to be on kinetic theory. Now, kinetic energy. Kinetic theory is very simple. When matter has energy, it moves really fast. When it has a lot of energy, I should say it moves. When it has a lot of energy, it moves faster. When it has less energy, it moves more slowly. Now, I am going to say things that you're going to want to take notes on because not everything is going to be on the board. The board would be even more random looking than it is now. But I'm going to get it on film so you can look at it and take notes. Clear? If you don't want to take notes now, that's fine. I would rather have your attention on me. If you see any mistakes on the board, tell me, and you can take a picture of the board for your own notes if you wish to do that as well. Now, temperature is based on kinetic energy. Because what happens with kinetic energy is molecules move. Yes? So far, up until and including chapter 12, we looked at chemicals, molecules, elements, atoms, etc., as something that's static on a piece of paper. Hydrochloric acid plus sodium hydroxide yields sodium chloride plus water. Nomenclature, equation writing, stoichiometry, everything was on a piece of paper. Everything was static, non-moving. Now, we're getting into, let's put the molecules in motion. And what you're going to do is, you're going to create a physical environment that will affect chemical reactions. So why are we studying physics? This is physics. It's physics. It's not chemistry. It's physics. Why are we studying physics? Why are we studying gas laws? Pressure, fluid dynamics, crystallography. Why are we doing that? It's not chemistry. The reason we're doing it is because chemical reactions don't take place in a vacuum. They take place in nature. They take place in a laboratory. They take place at room temperature. They take place at STP. 1 atmosphere, which is 760 millimeters of mercury, or 101.5 kilopascals. I'm going to explain where kilopascals and millimeters of mercury come from. So we have to study pressure and temperature because those things affect the environment in which chemical reactions are occurring. Because chemical reactions are happening with and alongside the kinetic theories. Which means that, and a particle theory, which means that matter is made of particles that move because of energy. And that energy of motion is called kinetic energy. Let's look at work. Let's look at work. Let's look at kinetic energy, and let's look at potential energy. Okay? And I have some people that are going to give us definitions from the internet on work and heat and energy. Mas, you have some stuff? I'll ask you in a minute, okay? So I just want to look at something that's very telling. I want to do a dimensional analysis. Many chemistry teachers will say dimensional analysis is, converting from volume to mass, going through moles and crossing out. That's not dimensional analysis. That's factor label, cancellation, unit label conversion. This is dimensional analysis. The weight of something, the force, the weight, is mass times acceleration. If I say the weight, that's gravity. That acceleration is g. That acceleration is very specific, 9.8 meters per second squared, or simply rounded to 10 meters per second squared. I always use 10 when I teach physics. Clear? But force, this weight, like pounds in America, weight is actually mass times acceleration. You take the mass of the object and you multiply it by the acceleration due to gravity, and that's the weight. Now, if I'm moving horizontally and I apply a force to a 1 gram mass and I'm only accelerating at 2 meters per second, then it's going to be, I'm not using g, I'm using whatever a I'm using. But this is, I'm just using g as just an example. A could be anything. But if it's vertical, up and down on Earth, you use 9.8 meters per second squared, or simply 10 meters per second squared. Mass times acceleration, 1 kilogram times that acceleration is 10 kilogram meters per second squared. Clear? And the definition of kilogram meter per second squared is a Newton, after Sir Isaac Newton. Unit labels that are named after people are capital letters. So capital N. Clear? Yes? Now, work is force times distance. There's Newton. Work is force times distance. So that's going to be Newton, force, times distance, meter. I know that Newton is kilogram meter per second squared times meter. Correct? So that's going to be kilogram meter squared per second squared. Easy? So don't let anybody ever tell you that work isn't energy. It's energy. It's mechanical energy. Now, there's a lot more to it than that, but that's good enough for now. And I'm going to tell you why it's energy. I'm going to show you. You may have seen, how many people have seen this before? Kinetic energy is 1/2 mv squared. Okay, we have a couple of hands. Okay. Well, let's look at the unit labels for that. See that ever before? 1/2 mv squared for kinetic energy? Okay. It's kinetic energy. That's the equation for kinetic energy. M is mass, not meters. M is mass, right? Okay. So that's going to be kilograms. Velocity is meters per second. Do you know that, Jen? Makes sense? Meters per second. Now square meters per second, what do you get? Musaba? You don't know? Square 2 over 1, what do you get? 4 over 1, right? 2 squared and 1 squared, right? Square 2 over 2, what do you get? 4 over 4, or 1, right? You get it? So when you square a quotient, you square the numerator and the denominator, correct? So if I'm squaring meters over seconds, I'm squaring the meters and the seconds, right? So square velocity is meters squared over seconds squared, correct? So that's what that is. Meters squared over seconds squared. You see that? Look at that. That's kinetic energy. Look at that. That's work. Look familiar? Potential energy. Has anybody ever seen potential energy? To calculate it's mgh. Anybody ever see it? Okay, we have some people here. We have somebody from Denmark. They do a lot of energy in Denmark. Excellent. Excellent. Are you just saying that because you're Danish and you don't want to look silly? He's just saying it because he's Danish. Okay, fine. All right. Now, so mgh is potential energy. Well, look at this. mgh, that's kilograms, meters per second squared, meters. So that's kilogram meters squared per second squared. Yes? What is the symbol for work energy? Do you go around saying kilogram meters squared per second squared? That would be a little bit boring, right? Instead of saying kilogram meters per second squared, we say Newton. Is there a name for kilogram meter squared per second squared?
Joule.
Joule. And there was a guy by the name of Joule. Okay? Mr. Joule. Yes? Okay. You want to look up something there, Mountis, on Professor Joule? We'll get a couple of sentences of information on him. Okay, so Joule, 1 joule, can you see this? 1 joule is 1 kilogram meter squared per second squared. So that's a joule. That's mechanical energy. How many people have ever heard of a calorie? Do we have any calorie counters in here? Anybody on a diet? Personally, you all look underfed, okay? You all look too thin, so you should go on a diet, okay? Master, you've counted calories, you're on a little bit of a diet? Okay, that's okay, it's fine. I'm on a diet. I have diabetes, I'm on a diet. Can't have that, right? Gotta control things, right? Watch your sugar intake, even now, so you don't develop type 2 diabetes when you're older. Not good. We'll talk about that, too, a little bit later, diabetes and how to control it relative to calorie intake, yeah? Now, so we know that 1 kilogram meter squared per second squared is 1 joule, correct? Well, 1 joule is 0.239 calories. And what we use is essentially 1 calorie is 4.18 joules, same thing. 1 calorie is 4.18 joules, or 1 joule is 0.239 calories. Memorize that. Do yourself a favor, okay? Yes? Now, look at that capital C. Believe it or not, that's important. 1 capital C is 1,000 little c's. This is a dietary calorie. This is a scientific calorie. You get it? Yes or no? 1 kilocalorie, small c, is 1 large C calorie, 1 dietary calorie. So 1,000 dietary calories is 1,000,000 scientific calories. Amazing, isn't it? So relative to the human body, in terms of heat, you don't really work with joules, you work with kilojoules. Right? You get it? Because 1 dietary calorie is 4.18 kilojoules. You get that? 1,000 scientific calories in a dietary calorie. 1 scientific calorie is 4.18 joules. 1,000 scientific calories is 1 kilojoule. 1,000 joules, 1 kilojoule. So 1 dietary calorie is 1 kilojoule. So 1,000 kilojoules, that's really what we use. We don't really use joules, we use kilojoules. When we're talking about, if you want to talk about diet relative to joules, it's really kilojoules you're talking about. But people don't really use kilojoules in their daily life. They use kilocalories or dietary calories. Clear? When you say kilocalories, you really mean 1,000 scientific calories. When you're talking about diet and you say 1 calorie, it's known to be 1,000 scientific calories. So it's just lingo and vocabulary and knowing the situation. Right? Sabi, you're taking copious notes over there. There's more paper in the back if you need more paper, if you run out. You look like you've used 1,000 pages already. It's amazing. Okay? I know. You got to lighten up a little bit, okay? You know, watch that heart. Excellent. Okay, you don't want to overuse it. Excellent. Okay, now, so, where are we? All this stuff. I think... Oh, I know. What is hot and what is cold? Now, I went through this with everybody, so everybody seems to know. Nobody knew what hot and cold was. If you're watching this and you have no idea who I am, you probably think I'm crazy. And maybe people in here are just going to tell me what they think I want to hear and don't believe me. But, Jen, what's cold mean?
It's just a feeling.
It's just a feeling. It's just feelings, nothing more than feelings. It's a sensation. It's a result of heat crossing nerve endings. When heat leaves my hand, if I'm warmer than the environment, it's 0 degrees outside and you go outside with shorts and a t-shirt. Are you going to feel cold?
Just a tad.
You're going to feel cold. Well, maybe someone from Denmark isn't going to feel cold. Okay? But area of high concentration to area of low concentration. That's how heat travels. Heat doesn't travel from cold to hot. Heat travels from hot to cold. What you would say hot to cold. Heat travels from regions of high concentration, 0 degrees outside, t-shirts and shorts, I'm going to feel cold. Area of high concentration to area of low concentration. Yes? So I'm going to feel cold. Why am I going to feel cold? Because the heat is crossing the membrane I call my skin. It's going out. So it's going to feel cold, that's human, that's circle. When heat leaves, that's cold. If I put my hand over fire, where's the area of higher concentration? The fire, the plasma, the fire, or my hand? The fire. So where's the heat going to travel? Is it going to travel out of my hand into the fire? Or is it going to travel from the fire into my hand? Kinga. It's going to travel from the fire into my hand. So that is the definition for hot. Hot and cold are really sensations. This is what the dictionary should say about hot. A sensation whereby heat flows from the environment across the skin of a human into a human. Because we humans define hot and cold. Those are human words. So that's what it should say. Have you ever heard, does your dog tell you that it's hot? Have you ever ridden a horse and it sweats and you get off the horse and the first thing the horse says to you, man, it's hot out here. Does it? Musaba? You have camels talk to you saying, man, it's hot out here, Musaba? Do they? No. Mwasa, do they? You have camels in Jordan? Do they hang around in clusters and talk about how hot it is outside? No. Humans. So, that's what it should say. It should say, energy, hot is energy going from the environment into my skin, through my skin into my body. Cold should be defined as energy leaving my body going across the skin to the environment. Area of high concentration, outside. Area of low concentration, inside, hot. Area of high concentration inside, area low concentration, cold, leaves my body. What's the difference between a heat burn or a hot burn and a cold burn? Absolutely nothing. It's a dehydration. When you dehydrate the skin or the body, you're burning it. Burns, blackens. You ever see, I'll show you some pictures of severe frostbite. And it looks the same, looks black, it looks blah. Okay? Yes? Enough said? Yes? Okay. If you ever see somebody yelling from their feet getting frostbite, the feeling that they're feeling is like putting their feet in boiling water. It hurts. I told the class, I climbed up Mount Etna, tried to, but I had sneakers on and I got terrible frostbite. I didn't lose anything, didn't turn black, but it hurt, man, I'll tell you, it hurt. And I spilled bacon grease on my foot as a kid. and God, I was screaming. You know how it felt? Exactly the same. It is exactly the same. Had it on my hands, just painful, painful, terribly painful. Yes?
Is that why you don't feel your feet anymore?
No, that's something else. Yeah. So, now, next, long lecture. Okay? We're going to quit in a little bit. I want to talk about pressure. Okay? I want to talk about pressure. Okay. Now, should I erase some of this? Make it easier to see? Yeah? So I'll erase this. I'll erase this. I'll erase this. I can erase this. I can erase this. Is that good? I can erase this. Okay. All right, before I talk about pressure, let me talk about change of state. Okay? This will take just a moment. All right? One more thing I have to put on the board for this. Has anybody ever seen ice melt? Raise your hand if you've seen ice melt. Excellent. Raise your hand if you've ever seen water boil. Okay, good. This is a graph of water, of ice. Let's say this is -20 is degrees Celsius, and let's say this is +120. Okay, is that okay? So ice at -20, it's going to heat up. Kinetic energy is increasing. Okay, it's going to heat up. It's going to get to 0 degrees. What's going to happen at 0 degrees Celsius? It's going to melt. Yeah, it's going to change state. How come there's no temperature change? It's a little weird. Is it gaining heat? Yeah, it is. It's gaining heat. It's gaining the heat of fusion. That's what it's called. The heat gained in the change of state from solid to liquid is called the heat of fusion. It is not kinetic energy. It is, it's a potential energy. In other words, you're going like this, that's the solid. And you're gaining potential energy, and you're increasing the distance or just MAD. You're just increasing the distance in which the molecules find themselves. So you're increasing that distance, so you're increasing the potential energy. Do you understand, Masa, that molecules in a solid are close together relative to a liquid? Yes, she does. Do you understand that, Mohammed? You sure? Excellent. And that's what happened. When you increase the distance going from a gas to a liquid, you are increasing the potential energy. So that's what that plateau is from. When you go from a liquid to a gas, you're increasing kinetic energy. This is going to be, you're increasing kinetic energy. You're increasing kinetic energy. You're increasing kinetic energy. Yes? Here, you're increasing potential energy. Here, you're increasing potential energy. So when I get to a liquid, and then it heats up to a gas, and it's a plateau, it's called the heat of vaporization. The heat of vaporization. The heat of vaporization. Heat of vaporization is the potential energy that water, liquid water, absorbs, or any compound or any substance absorbs to transition between a liquid and a gas. Easy? That's what it is. Heat of vaporization is the heat necessary for that phase change from a liquid to a gas. It's an increase in potential energy. So you're going from this to this. What's greater? What's greater? The distance between ice molecules and liquid molecules, or the distance between liquid molecules and gas molecules. What's a larger difference? The distance between solid and solid and liquid, or liquid and gas? Liquid and gas. Liquid and gas. Look up, somebody, look up the heat of vaporization of water and the heat of fusion of water. Doesn't matter what unit labels you use as long as they're the same for each, okay? And then I'll report that. All right? So the heat required to go from a solid to a liquid without a change in temperature is called the heat of fusion. It's a potential energy increase. The energy needed to go from a liquid to a gas without a change in temperature is called heat of vaporization. It's another form of potential energy. It is not kinetic energy. Do you understand? It's definition. We'll actually maybe even do a lab on that. It's very important to understand. Okay, so I can erase now this. You see, heat of fusion, heat of vaporization, no change in temperature is 0, but you have a change in potential energy that's greater than 0. It's not 0, but it's greater than 0. Clear? Okay? All right. Now, let me erase this. 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 Now, I just want you to, I want to draw this with a little bit more proportionality, okay? Let's say I have, we can use another marker. Let's say I have water, and it's negative, this is 0 degrees Celsius, it's negative 20. This is 0, this is 100, this is 120, this is 0, okay? This is where it starts. You go up, it's actually a very small plateau. Did we get anything mounted yet? Okay. And then we go up to here. This is a very long plateau. Okay. This is 6 to 7 times greater. It's like, I'm guessing, if I remember correctly, the heat of fusion is like 80. Is that calories?
Grams, yeah.
Is that what does it say?
The heat of fusion for water, calories grams is 79.8.
So 80. So 80, and what is that in?
Calories.
80 calories per gram, right? Or 80 kilocalories per kilogram, right? Now what's the heat of vaporization? It's going to be 5 something, 580, 560, 540. He's going to get back to us on that. But the point is that the difference in distance, if I want to go like this, that's a solid, that's a liquid, and that's a gas. Very large difference. Okay, very, very large difference in distances. Yeah. So the potential energy increase is much greater going from a liquid to a gas. It's about 560-ish calories per gram. Notice I don't say calories per gram degree Celsius or anything like that. It's just calories per gram. Okay? Now, and we'll come back to that, but I want to look at pressure. Okay? Let's see how I'm doing in terms of seeing the board here. Let me leave it like that. Okay, good. All right, now, I essentially want to talk about, yes, do we have something? Yes, what do we have?
It's 540.
540, okay, that makes sense. I remember that now. 540 calories per gram, or 540 kilocalories per kilogram. Okay, very good, thank you. And what is 540 divided by 80? Somebody give me that? 540 divided by 80. 6.75? 6.8? So 6.8 times greater. All right, heat of vaporization relative to heat of fusion. 2 points. Pretty good, huh? Okay, now, so I'm going to erase this. Let's talk about boiling. Okay, now, let's say I have a eudometer. What's a eudometer? Somebody want to look that up for me? Eudometer? What is a eudometer? You're going to have to spell it. I'll give you a hint. EU. EU. Eudometer. Eudometer. What is a eudometer? Anybody?
Laboratory device that measures the change in volume of a gas mixture following a physical or chemical change.
Wow, very cool. That man's from Texas. That was quick. Okay? Read it and I'll read back. They're not going to hear your voice. What'd you say? Laboratory instrument for measuring the volume of gas.
The change.
The change in the volume of gas.
Of a volume of a gas mixture following a physical or chemical change.
Okay, so you have a chemical change and you have a change in volume of a gas and you have gas pressure, right? Change in pressure, right? So it's literally it's a graduated tube of some sort. The whole thing is graduated. But it's a graduated tube, open at one end, closed at the other. And let me show you several eudometers, okay? These eudometers here, looks kind of funky looking, right? Let's say that it's mercury, okay? Can I do that? Is that all right? Okay, that doesn't mean a lot to you right now, but it will shortly. Do you see that this gas here is trapped by the mercury? Do you see that the gas goes all the way down to right there? I'll make it black so you can see it. Goes down to here. You see that? You see that little red arrow? That's a continuation of this line. You see that? Yes or no? Yes? And there's a change in height. Yes? Yes? Okay. That change of height is graduated. So I can tell the actual height in length graduated, millimeters or whatever. In this case, they're millimeters, right? Yes? And I know that the gas pressure in here, isn't it greater than the outside pressure? Because it's pushing down on the mercury, isn't it? So look at this, look at this, look at this. It says pressure, this is gas pressure, equals the atmospheric pressure, that's what the red lines on the outside are, minus that height. Does that make sense? Is that okay with that? You're not quite sure how I did that, how you can just subtract the height from pressure. But I'm going to show you that the pressure of a fluid is dependent upon height, not area. I'm going to show you that, okay? Pressure is dependent upon height, not an area of a fluid. But I'll show you that not today, but I'll show you that tomorrow or the next day, okay? Now, Do you see that these pressure here is greater? The atmospheric pressure is greater because it's forcing the fluid up to right here. You see that? So the atmospheric pressure would be greater, wouldn't it? Right? So it's the atmospheric pressure plus that change of height, wouldn't it? Yes? Yes? Okay? Now, if they're the same height, the atmospheric pressure and the gas pressure would be the same, correct? Yes or no?
Yeah.
Whatever kind of gas it is. I mean, it's not necessarily air, it's just a gas. Okay? You get it or not? Mark said it. It's an instrument used to measure the change of pressure of a gas due to a physical or chemical change, physical or chemical reaction. It's graduated tube, closed at one end, opened at another. Yes or no? Yes? Okay. Now, let's say I take a tube of mercury, a eudometer full of mercury, right? Full of it, right? So I'm going to take a eudometer and I'm going to fill it with mercury. Okay? I'm going to fill it with mercury. Is that okay? Can I do that? Yes or no? Yes? I can do that? Okay. And I'm going to put my finger in the top. I'll use gloves. Years ago, we never used gloves. It was amazing what we did with mercury. You take it, and I'm going to put it in a large, deep tray full of mercury. So no mercury can escape. Right? Is that okay? And the mercury may fall, right? But inside the tube is what? Is that a gas? Inside the tube, if it falls, it's a vacuum, right? Okay? So now I'm going to put it in a tray filled with mercury. So I'm going to take it and I'm going to turn it upside down and put it in the tray. Okay? Is that okay? Can I do that? Now, isn't the mercury is very heavy. Mercury is 13.6 times more dense than water. The density of mercury is 13.6-ish. The density of water is 1-ish. Okay? Are you all right with that, Kamal? Excellent. Now, what's going to happen is this. Let's get a better shot of that, okay? Can somebody look at that and see where it's coming? Am I getting a better shot of it? Is that good? Is that good? How's that? Really good? Like really good? Is that good? Okay. Ava, the videographer, is giving us the okay. So that's what you get. Now, this is atmospheric pressure. Has anybody ever heard of atmospheric pressure in inches? Like 28.6 inches today? Mark from Texas? That's like an American thing. Okay? It's an American thing. This is 760 millimeters of mercury, right? Or 76 centimeters, right? What's 76 centimeters divided by, can you see right here? 76 centimeters divided by 2.45. What does that equal? What does that equal?
31.
Is that right? 31-ish? 31 inches. So, yes.
I believe an inch is 2.54.
Sorry, 2.54. Thank you. Excellent. Dyslexia. Thank you, Mounds. Extra credit. I like that. Excellent. 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 2.54. That 31 seemed a little high. I thought it was like 28 something. So what is 76 divided by 2.54? Yes.
29.92.
28.9?
29.
29. So I really don't know my stuff, do I? I know, I'm getting away from English American unit labels. Kind of scary, isn't it? So what would you say it was? 29 point what?
29.9.
29.9 inches. Okay, so that's 1 atmosphere. If I did this at 1 atmosphere at sea level, right? And it was an average day, it would be 1 atmosphere would have that pressure. In other words, the atmosphere would keep the level of mercury up the tube 76 centimeters or 760 millimeters. So 1 atmosphere is 76 or 760 millimeters. Do you understand that? Eudometer? Yes? So what is 76 centimeters times 13.1? What is 76 centimeters? No, let's do it. Let's just do it in meters. 0.76. I'm going to erase this. What is 0.76 meters times 13.6?
10.3.
What is it?
10.336.
10.3? If I used water instead of mercury, this height would be 10.3 meters. What is atmospheric pressure in pascals? We talked about this Sunday. 101.3 kilopascals-ish. Yes or no? Ish. Somebody want to give me an actual reading from the book? I don't memorize stuff in chemistry. Have you noticed? I just look it up. Okay. Now I want to move this over here.
It is 101.3.
What is it?
It is 101.3.
101.3? All right. I'm going to move. I'm sorry if this is going to make you dizzy when you're watching this. Let's see if we can move this. Excuse me, Jen. I'm sorry. I want to get the whole board here in. How am I doing? Does it look good? All right. We want to move this way. Where are my glasses? Here they are. All right. So I want to move like this. How's that? That looks pretty good, huh? Yes? All right. Now that everybody's all sick from that movement. Okay, looks good. Okay. Now, I'm going to show you a few things. Where they get 101.3-ish kilopascals. Okay? Yes? Now, pressure is in pascals. But do you have a feeling that it really equals something else? And that just 1 Pascal is just a convenient way of saying it. In other words, kilogram meter per second squared is a Newton. Kilogram meter squared per second squared is a joule. What's a Pascal?
I'm thinking, and I'm not sure if this is correct.
Go ahead.
A Newton over square meter.
How did you know that? Oh my God! God bless Colorado. Wonderful. 2 points for the team from Colorado. -2 for Ethiopia. He's never used the calculator before. He doesn't know how to hold on to it. So, yeah, that's right. She said that a Pascal was a Newton per square meter, and that is absolutely correct. 1 Newton per square meter is a Pascal. Okay? 1 Newton per square meter is a Pascal. Yes? Is that okay? You all right with that? Okay, now. Let's say I take a cubic meter. Cubic meter. Right? And I fill it with water. I fill it with 1,000 kilograms of water. That's going to be 2,200 pounds for the Americans in the class, or 1 metric ton. Okay? Yes? Is that okay? What would the force of 1,000 kilograms be? What would the force of it be? Remember, mass times acceleration, we're talking about a weight. What weight would it have? What's the acceleration due to gravity? 10. So what's 10 times 1,000? Lizzie? Okay. Well, can I finish up? Okay. I want to finish up, but thank you very much. The class is over and they're just being so kind to me. Okay, and then just let me finish my sentence. Excellent. Okay. What did I say? What did I say?
What's the force?
Oh, wait, what's the weight? What's the weight? The weight is 10,000 newtons, right? Because it's mass times acceleration. Do you remember I said over there that force equals mass times acceleration? Mass of 1,000 kilograms times 10 is 10,000, right? Yes? Yes? So that cubic box is 10,000 what? Newtons. I'm almost finished. Almost finished. 2 more sentences and I'm done. If I stack 10 of them on top of each other, what's 10 times 10,000? 100,000. It's 100,000 newtons per square meter, isn't it? It's 100,000 newtons per square meter. It's 10 meters. Didn't I say that the equivalent of the height of a eudometer of mercury in water is going to be 10.3 meters-ish? Well, that's what it is, 10-ish. Yes? That's where it comes from. So what's 10 times 10,000? 100,000. 100,000 pascals, or 100 kilopascals. Do you see where 101.3 comes from?
Yes.
It comes from newtons per square meter. We're looking at air in terms of water. The column of air in water would be like this. Tomorrow, or the next day, or the next class, I'm going to do it in terms of the density of air, which I happen to know. It's a little scary, okay? Have a great day. Sorry.